Hey everyone, welcome back to Code Studio. In this video, let us start with our new series, a much deeper and famous example of recursion, Fibonacci series. A very important thing I want to add is that the discussion about Fibonacci series might become large, and also it acts as a link for us between recursion and memoization, or the most famous dynamic programming. Hence, the series on Fibonacci series is aired in a separate playlist and not in our recursion playlist. Since it acts as a connecting link from the topic recursion to yet another interesting topic, dynamic programming, we would also be starting on a new journey with dynamic programming in the coming future. I have added the Recursion Series playlist in the description below and view it to know about recursion in detail. This series on Fibonacci gives you a complete understanding of the different approaches to solve this problem, recursive, iterative, and memoized, with complete analysis on all of them. So stay tuned to Code Studio for the coming parts on Fibonacci series. Now let's get going with our video. What exactly is Fibonacci series? Fibonacci series is a sequence of numbers that go like 0, 1, 1, 2, 3, 5, 8 and 13 and so on. Obviously, this is an infinite sequence of numbers. The main running principle of this sequence is that the number in the sequence, that particular number, is the sum of its two last preceding numbers except the 0 and 1. The 0 and 1 that are at the starting of the sequence are actually the default values, and they are not to be changed, or they don't have a particular principle of appearing in the sequence. They are the default values kept inside the sequence, and the upcoming numbers after 0 and 1 actually follow a principle. That principle is that that particular number is obtained by adding the last two preceding ones, right? So to understand what exactly is this, let us analyze this series 0, 1, 1, 2, 3, 5, 8, 13 in that given light of view. So let me start with the default values 0 and 1, which are to be there for compulsory, and then let us say I have to fill in the numbers. What I will do exactly is I will fill these numbers based on the principle that Fibonacci series actually follow. So this particular number should be the sum of its last two preceding numbers. So the last two preceding numbers for this particular index are nothing but 0 and 1. So the sum of them would be obviously 1. So I'll fill in 1 here. And then the last two preceding numbers for the number at this index would be these both, 1 and 1. Hence I'll fill in my number to be 2 here. 1 plus 1 is 2. In the same way, at this index would be sum of these two values, 2 and 1, so that would be 3.
And then 3 plus 2, 5, 5 plus 3, 8, and 8 plus 5, that is 13.
So this is how the Fibonacci series is basically generated. You get the point, right? A number at particular index is actually the sum of the preceding two numbers. So the main motto is to generate a recursive algorithm or a recursive function to find the number at this particular index. Let us say my indices start and go in this way as follows, like 0, 1, 2, 3, 4, 5, 6 and 7. Let us say these are my indices. So if I say I want the value at third Fibonacci index, then my answer would be 0, 1, 2, 3. So my answer should be 2 in this case. We have to generate a particular recursive function that gives out the value at that particular index n. So this I is actually n in our discussion. Before we move further, to know what exactly is recursion, how to write a recursive function step by step has been explained in my earlier videos. I'll be leaving the links in the description below. Go check out if you want to know more about recursion in detail. I've also explained a few examples and their step-by-step procedure to write down the recursive algorithm. So let's get going with our Fibonacci series recursive function. To understand how recursion actually works in this problem, let us write down the main mathematical principle that brings us the Fibonacci series. Since 0 and 1 are our default values, they form our base case to recursive algorithm, because they are the places where our recursive algorithm stops and returns a default value, that is a particular given value. And for other values we have to generate a recursive code. First, let me declare the function. The function would be fib of n, and this function has two cases, the recursive case and the base case. And the base case would be when n is less than or equal to 1, right? When n is less than or equal to 1, a function would return a value of n. See, when n equal to 0, a function should return a value of 0, and when n equal to 1, a function should return a value of 1. We are not taking in case of the non-negative integers. That would be not considered, because we are assuming that only non-negative integers are given as input into our recursive function. To handle the non-negative integers case, we'll just return an EOF value when n is less than 0. When n is less than 1, we would actually be returning the value of fib of n minus 1 plus fib of n minus 2. This is what we have discussed as a main principle for our Fibonacci series. The sum of the last two preceding numbers of this particular nth place. When the integer is at nth place, then the n minus 1 position is this and n minus 2 position is this. So the sum of numbers at this positions sum up, and this summing up and gives us this value as 13, that is fib of n. So now let us move on to a code editor and write our code and check whether this particular algorithm is working fine or not. The code for the Fibonacci is pretty simple. We have to just implement our recursive algorithm that we have devised into the code. So let me first write down the basic skeleton for both the C program and C++. So basically we would be inputting the index and then returning the value of Fibonacci of n, that is the index. That is basically the value in the Fibonacci sequence at that particular index. So we haven't yet declared the function fib, which we would be doing now. So int fib, and this would be taking an integer n as an input, and then we would be first writing our base case, which is nothing but if n is less than or equal to 1, then our code should return a value of n. When it is n equal to 0, then 0. If it is equal to 1, then 1. And else we have to return the value of Fibonacci of n minus 1 plus Fibonacci of n minus 2. Since the function declaration and the if conditionals is exactly same in both C and C++, I'll be just copying this stuff and using in the C++ program too. So this is perfectly fine. Before actually compiling and running the program, I'll be writing down the Fibonacci series so as to cross check when I run the program. Let me also write down the indices. So let me compile my Fibonacci recursion.c first, and let me run my program. The answer at the value index 1 would be 1, at index 2 would be 1, at index 7 would be 13. Fine. Now let me compile my C++ program. 1 1 let me say 6 8 and then 8 21. So our code is running perfectly fine without any errors. So this is how you actually code for the recursive function for Fibonacci numbers in C and C++ respectively. Now that we have seen our code is running perfectly fine, let us now actually analyze our given problem, whether it is time efficient or space efficient to actually use a recursive algorithm in this case. So to make our analysis clear, let me explain you how the algorithm occurs beneath our eyes using the tree method of this Fibonacci series. Every time I am depicting the function in our tree call, I'll be not using the fib every time, because that is actually mundane to use fib every time. So I'll shorthand it to a normal function that we use in mathematics as f of something, or f of n is a recursive function instead of fib of n. Fine. Let me explain you the process that actually occurs beneath our eyes of f of 5. So let me start with f of 5. So f of 5 first calls, since 5 is not less than or equal to 1, then it calls f of 4, and it should also call f of 3. But since f of 4 isn't actually returning a value to f of 5, we'll be going on with our calling stack in the function stack. The value of the function should pop out, then only another function will push into the stack. Fine. So then f of 4 will be calling in f of 3, and f of 3 would be calling f of 2, and f of 2 would be calling f of 1. Here our solution actually starts giving some results. F of 1 returns a value of 1 to f of 2. So when f of 1 returns a value of 1 to f of 2 pops out the function f of 1 and calls in the second function f of 0. And f of 0 also gives out the value of 0 to f of 2, and this actually sums up and a value of 1 comes at f of 2. And when f of 2 returns a value of 1 to f of 3, the function f of 2 pops out and f of 3 would be calling in the another function, that is f of 1. So this is how the popping out of functions and pushing in of new function calls occur in the function stack of a recursive algorithm. So every time I am discussing this particular course of tree diagram, I'll be not using the popping out and pushing in of functions because that actually takes a lot of time. Let me actually go on with the normal usage of words. So f of 1 generally returns a value of 1 back here. This sums up to 2, and 2 returns to f of 4. F of 4 calls f of 2, and f of 2 calls again f of 1. This returns 1 to here,
and then it calls f of 0, and then 0 gets to f of 2. This word gets summed up, and 1 returns here, 1 goes here, 2 plus 1, 3.
and again f of 5 calls again f of 3, f of 3 calls f of 2. So the values of f of 4 and f of 3 are written to the function f of 5 as 5, and our 5 is returned to our solution. So this is how the function call occurs for this recursive function. This is pretty clumsy in looking here. So let me actually clean this stuff and draw the tree diagram in a neater and cleaner way. This is how the recursive tree actually looks in a more cleaner way. So what exactly is the problem in this method of solving the Fibonacci series? So the main problem occurs, so we can actually go into the bigger notation of time analysis and space complexity, but before that let us actually logically understand why this particular recursive algorithm is not efficient. As you can see from this given calling stack, we calculate the value of f of 3 twice. See, we do the same thing. I guess I missed an f of 0 here. Yeah. So we are calling this f of 3 the same thing again. We'll be calling f of 2 and f of 1, f of 2 and f of 1, f of 0, f of 1, f of 0, f of 1. This whole calling stack gets called twice out of no reason actually, right? I think I missed another f of 0 here. Oh, why am I missing f of 0s? Okay, that's fine. So out of no reason we are calling the same thing again and again. This is fine for f of 5. We are only calling particular thing twice. But let us say if it is f of 100, then we have to call f of 98 twice. And inside f of 98 again we have to call f of 96 4 times. So this becomes pretty large again. See, every time we have to call in the same thing again and again out of no reason. This is not efficient, right? We are programmers. We have to always think out of an efficient method to solve the code, not to use an inefficient method when there is always an efficient method to solve this code. So the time complexity of this particular recursive algorithm has a big thing to calculate and prove that it's 2 power n. But let me give you a brief insight on this. We would be observing for different values of f of 5, f of 4, f of 3, f of 2 of such sort, and then we would actually be doing some approximations, and we found out that the lower bound of this value, or lower bound of the time complexity of this particular recursive algorithm, is O of n by 2, 2 power n by 2, and the upper bound is 2 power n. Since we would be taking the worst case scenario, our time complexity for this recursive algorithm is O of 2 power n. This is pretty insane because we are having an exponential time complexity for this recursive algorithm. How can we improve this particular algorithm? We have a better algorithms to solve this Fibonacci series, and we will be discussing in the next videos on playlist Fibonacci series on codestudio.saiankit. And we can say that the space complexity is also not so efficient for this recursive algorithm. Not always recursive algorithm is efficient. We have to always see the time complexity of a particular algorithm we devised. Is it really better as compared to its iterative algorithm, and is it really worth it to use that particular algorithm? And then we have to go on to code for a particular problem, because time is a main key factor, and as programmers we have to keep in mind the time complexity and space complexity of algorithm that we are choosing to write. Undoubtedly, this recursive algorithm is not cool, inefficient to be precise. We have a very good efficient algorithms as compared to this recursive algorithm, and then we'll be discussing in the coming up videos on this particular playlist. Until then, bye. Signing off, Saiankit, Code Studio.